My research is in the connection between machine learning and stochastics. So basically what I want to try to do in this talk is to first give you a bit of an introduction into machine learning, so machine learning 101, then give you a bit of introduction about stochastics, so basically what you will learn in the first course of stochastics in your third bachelor semester, and then try to combine the two, and in the end I will talk a bit about my research, but mostly the aim is to make the connection between stochastics and machine learning. And so machine learning and artificial intelligence is a very nice topic for people doing stochastics, because basically every machine learning method is using some kind of randomness. So I brought you two simple examples. The first one is for large language models. So for example, you have a problem and you don't know what you should do, and then you ask ChatGPT, and ChatGPT gives you an answer. But it doesn't give you always the top answer or the answer that is like most commonly given. Sometimes it gives you the second best option or the third best option, and this makes actually ChatGPT much more human-like. So for example, a common problem, so it's Friday afternoon and there are two possible options. You can go to a party with your friends, or you can write a mathematical paper. And then sometimes ChatGPT tells you to just join them because social opportunities are time-bounded and non-recoverable, and attending the party preserves social capital and reduces burnout. So this would be one possible option. And the other one is just write the paper, because there are some deadlines, and yeah, the paper has material consequences for your academic standing. So you should write the paper and then go to the party maybe afterwards. So this is very important that ChatGPT switches a bit up the possible solution, because imagine a world where you give a large language model, should do all your decision-making processes, and then every time when you ask the question, it gives you always the same answer. So for example, it always tells you to write a paper, then probably my wife will be very mad at me, and rightfully so. So it's good that it switches up between the possible solutions. And then the second example is for generative models. So for example, if you want to, your artificial intelligence, you want to come up with a comic of a professor that explains the law of large numbers, then drawing a comic or a picture is very a creative thing. So everybody sees the world a bit differently. So it's very good that ChatGPT gives different answers and different ways of viewing the reality, of viewing the world. Maybe it's a bit problematic that in 8 out of 9 realities, the mathematics professor is a white male, an old white male wearing glasses, but it's a problem for different talk. But here also you give ChatGPT the same task, and it gives you a different output. But in this talk, I want to focus on the randomness in training and in the training process of training a neural network. So first, let's fix a very basic supervised learning problem in machine learning, and tell you how you can see randomness in the training process. So here's the task. So let's assume that you want to have a program which tells you the fair market value of a house. So you want to come up with a function where you plug in all the data that you have about this house. So you know how many bedrooms there are, how many square meters there are, in which city it's located. You have all those data. And then you want the program or the function to come up with a fair market value of this house. Okay, so you want to learn somehow a function where you plug in all the data that you have and you get a fair market value. So this function can rely on sales that you've seen in the past. So you can go to your favorite website and see for what price a certain house goes for. So you have accumulated all your data points, xn, f of xn, where xn is always for a certain house all the data, so all the number of rooms, cities, so on and so forth. And f of xn is the price where the seller and the buyer, they come together and they thought, okay, this is a fair price. I can sell the house for this specific price. So you have all those data points, and now you want to come up with your program, your neural network, that when I plug in my new set of data points, or my new set of information about a house, it gives me a price which would be a fair price of this specific house that I haven't seen before. So what do you do as machine learning applicant? You come up with your neural network of a neural network. Basically, a neural network for you is just, you don't have to know what this is specifically, but basically you have a huge parameter vector theta, which would be all the weights and biases in your neural network. And then if I fix this theta, so if I fix all the weights and biases in my network, I get a function. And this is this n of theta. And now the task is to come up with a function, so with a parameter vector theta, where the output of my neural network, so n of theta, should be close to the function, to the true function value alpha. Okay? So how can I decide whether my neural network is a good neural network? So I plug in the data point that I already have. Okay? So I plug in the data for the houses that were already sold, and I compare the true market value, which would be f of xi, to the output that my neural network would give. So this is n theta of xi. And then I look at basically the average error that I do. So I compute the square distance between the two prices, and then I take the average. And now we've reduced the problem of optimizing a neural network. In our specific task, we've reduced it to minimizing a function. So this is basically for every theta parameter, this gives me an average error, and I want to make this average error as small as possible. So what do? I have to minimize this function. Okay, and typically this is done by stochastic gradient descent or any other variant of this. So typically you would, in machine learning, you would hear the name Adam or something like this. Okay, so let's minimize this function. Typically what you would do is you come up with an iterative algorithm. So you initialize your neural network at some point, theta naught, and then you come up with an iterative scheme. And what you do is, at your current iteration theta k, you start at your current iteration point, and then you go in the negative direction of the gradient for a small step size. So basically, you compute the gradient, which in this task we can explicitly do, and then we go in the negative direction of this gradient with a small step size gamma. And so basically, you can think of this as a discretization of a gradient flow trajectory, and hopefully you find a critical point or good minimum while doing this. So for this empirical risk minimization supervised learning task, we can explicitly compute the gradient. So what would be the gradient? The gradient would be, this is an average of some errors. So I take, for the gradient, I can just take the average of the gradient of the individual functions. And then the gradient of the individual functions would be 2 times comparing the answer of your neural network to the true market value, and then times the gradient of your neural network. So this is something that you can compute, because for your data set you have the fair market price values. You can come up with the function values of your neural network, and hopefully you design your neural network in such a way such that you can compute the gradient. Okay, so this is what you would do. But now there's one problem if you want to try to implement it on your computer. And the problem is that typically you have a large data set, so capital N is very large, so you have the knowledge of all the houses that were sold in the past. And also your neural network is very large, so let's denote by P the number of parameters in your neural network. This is also very large. So in order to compute this gradient, I have to compute N times P individual derivatives of this neural network. So this is very costly. And then typically what you can do in order to make it a bit faster, so in order to not take so much time in order to compute one iteration step, is you use the law of large numbers. So you can just, instead of computing the average of all the gradients, you can just choose IID, one of the gradients, and then since you now it doesn't cost you so much anymore, so you can do a lot of iteration steps, and so hopefully during your trajectory you've used more or less all the data points, and so hopefully it's still a good object. Okay? So now here's the stochastic part. So you can see the average error that you do with your neural network as the expectation of the error that you would do for one single data point, where you take the expectation with respect to the uniform distribution over all the data. So basically you choose all the data points with probability 1 over n, and then your average error will be the expectation of this random variable. Okay, and this you can also do for the gradient. And then the natural thing to do is, in order, instead of computing the gradient of all your data points in each iteration step, what you do is in each iteration step, you choose randomly one of the data points, compute this gradient. This you can do very fast. And then now you have the flexibility to compute a lot of steps, right? So here, now this becomes a stochastic object because this highly depends on the data that you choose during your optimization trajectory. And as a probabilist, what we try to do is we now derive law of large number and central limit theorem and things like this. So this was the machine learning part. Basically, we try to optimize a neural network for a supervised learning problem. And how do you do it? You have your stochastic gradient descent, which computes the gradient for a single data point. And this you do on, and hopefully you converge to a point where the gradient is 0, to a local minimum. Okay? So this is the machine learning part, and now as a probabilist, we are very simple people, so what we do is you give us a problem, and then we compute the law of large numbers and the central limit theorem. That's basically it. Sometimes we try to be fancy and also compute large deviation principles, but this is not part of the first course of stochastics, so let's keep it to the specialists. So now, forget about everything that I just told you, and let's just recall what is in stochastics 1 the central limit theorem and law of large number. So here it goes. You take independent random variables that are identically distributed, and they have the expectation, so the mean mu and the variance sigma squared. And then what you can do is you can, for example, roll a die and do this a lot of times, and then take the average of the results that you've seen. And in the long run, this should converge to the mean, to the average weighted over all the possible options weighted with the probability that this happens. Okay? So basically, you have a lot of random variables, you take the average, and this converges to the mean. Now, in order to compute this mean, you have to store all the simulations that you've seen in the past, and maybe you want to come up with an iterative scheme that only needs to store the current guess and the next simulation of your random variable. And this you can actually do. So you can rewrite this average, you can rewrite this as an iterative scheme, where in order to compute the next guess, you only have to know the current guess and the new simulation. So basically you start from your current guess, which would be theta n, and then you subtract theta n times 1 over n minus n plus 1, and you add the new simulation, also weighted with 1 over n plus 1. And this is exactly the same as taking the average here. But now now we've rewritten this as an iterative scheme, and this is exactly the way how we write stochastic gradient descent. So we can view the law of large numbers, taking the average, we can view this as a stochastic gradient descent scheme, where the step size now is 1 over 2n, and your loss function, r, is just a simple quadratic function. So basically, in our neural network setting, if you think of your neural network to be just the constant theta value that I plug in, so it's a constant function, then this is exactly the same situation as in the general law of large numbers that you would see in stochastics. Okay, so this is basically, you should take all your heuristics about stochastic gradient descent from the law of large numbers, because this is a very simple special case of stochastic gradient. Okay, so this is for the specific choice of step size, 1 over 2n, for the specific choice of loss function, which is the squared loss between my current guess and the true expectation that I want to converge to. The random gradient will be, I compare my current guess, I plug in the new simulation, and then I have the comparison. And this is my stochastic gradient descent scheme. And the law of large numbers now tells me that if I do stochastic gradient descent with these values, I will converge to the global minimum of this loss function r, because the global minimum is the expectation, it's the mean, mu, and the law of large numbers tells me that I converge to mu. Okay, so this is the law of large numbers. Now let's do the central limit theorem. So what does the central limit theorem tells us? It basically tells us if I now subtract the mean, and I don't divide by 1 over n, but 1 over the square root of n, then this converges to a Gaussian. So basically, heuristically, you would say that if you do a lot of experiments that are independent, or you have a large population, then a certain characteristic, if you do the right Riemann normalization, the distribution of this characteristic will look like the Gaussian curve. Yeah. So this is one interpretation of the CLT, and this is the most widely used. But there's another one, and the second one is important for stochastic gradient descent, because the CLT tells you how fast is the convergence in the law of large numbers. So basically, in the law of large numbers, we've shown that the mean converges to the true expectation. I can now subtract on both sides the mean, and then this tells us that the mean, the average over the simulations minus the mean converges to 0. So you can ask the question, okay, how fast does it converge to 0? Okay? And the solution is given by the CLT, because by the CLT now I don't divide by 1 over n, but by 1 over square root of n. And what I get is something which doesn't converge to 0, but it also doesn't explode. So I get a non-trivial limit. And so this basically tells us that the speed of convergence in the law of large numbers is 1 over square root of n. So this we can use for stochastic gradient descent. So this is our stochastic gradient descent scheme for this very simple example. And the CLT tells us that we converge to the mean, so to our global minimum, with rate 1 over square root of n. So basically, if I want to get an accuracy of smaller than epsilon, then I have to do 1 over epsilon squared gradient evaluation simulations in order to be epsilon close to the true. Okay, so this is the stochastic part. We have the law of large numbers, which tells us that the mean, the average converges to the mean, and then the CLT, which tells us how fast it converges to the mean. Now, this is the situation for a very simple objective function, which was exactly the squared function. So basically, the gradient is exactly a linear function. And now in machine learning, it gets more complicated. Yeah, the response of a neural network will not be a constant function, but something highly nonlinear. So it becomes more and more complicated. So this is a visualization of the loss landscape for training a neural network, and this is, I mean, basically I projected it on a two-dimensional space because it's highly very high dimensional. And so if I take the step sizes that I would get from the law of large numbers, so I take the step size is 1 over 2 times n, then you can see a problem. And the problem is if you initialize very badly, you initialize very far away from like your good neighborhood, from a critical point, and you have to move actually, you have to move in this direction and get to the region where your critical point is, then the step sizes, they are very small. So they don't really get you anywhere. So basically you can assume that the gradient is bounded. And then how far have I traveled after n iterations? I basically have traveled a constant, which is given by the upper bound of the gradient, times the sum of all the step sizes that I took. And if I take step sizes that scale like 1 over n, then the distance that I've traveled scales like log n. So it's very slow. Okay, so typically in order to make this not only an optimization method which works well locally, but can also travel to another region, I want to take larger step sizes in order to first really move around, and then when I'm in a good neighborhood, I want to stay there and convert to a critical point. Okay? So now let's take larger step sizes. So something like not 1 over n, but n to the power of minus gamma, where gamma is strictly smaller than 1. It's between 1/2. Okay, and now let's do again the heuristic from the law of large numbers. So for this very simple function, so this one where we had the CLT, but now with this larger step sizes. Okay? So here's again the situation. So this is again this very simple function. The gradient will be just a linear function. I do stochastic gradient descent, but not with the scaling where I get exactly the law of large numbers, but with the step sizes that decay much slower. And what do I get? I don't get the true Cesaro mean, so I don't get like 1 over n times the sum of all simulations, but I get something like a weighted average, where basically, because the step sizes, they decay very slowly, older observations are less important to me, and newer ones I take more weight on them. So this is not really the law of large numbers that we are used to, but still it's somehow an average between simulations that we've seen, but now weighted differently. Okay, and you can compute now, this still converges to the mean, but it converges slower to the mean. Yeah? So now this doesn't converge like 1 over square root of n. Now it converges like n to the power of minus gamma over 2, and gamma was strictly smaller than 1. So this is slower than the CLT, which tells you the convergence of the true law of large numbers. This is slower, because we've taken larger step sizes, and thus we've taken more weight onto some simulations and less weight onto others. Okay? So now we had the problem that we want to move, so we have to take large step sizes. But now this destroys a little bit the law of large numbers. Now as a true person from stochastics, what would you do in order to get now fast convergence? Any ideas? Yeah. You would schedule the step size? Yes, this is something that you can do. Let's keep to those step sizes n to the power of minus 1 over n to the power of gamma. Any other ideas? Basically, we always have two options. We can do law of large numbers or CLT. And now we've destroyed a bit the law of large numbers, so now let's do another law of large numbers in order to get it back. So what we now do is, instead of just outputting the last iterate, so just theta n, because this would be a law of large numbers where the weights are a bit strange. Now let's output again the average of these iterates. Yeah. So basically, theta n is already a weight of all, an average of all the simulations that you've seen, but weighted a bit strangely. But now let's take another average over all the iterations that you had in your past, and you can compute. Now this is again an average of all the simulations, but now the weights have somehow balanced out, because basically in theta n your last simulation was very important, but now theta n in this average down here, theta n only appears once. Yeah, so the last simulations, they have very high weights for the thetas, but they only appear in a few sums of the average here. Okay. So we've done another law of large numbers. The theta themselves, they can travel far, but now locally again we get the best rate of convergence. So we get the law of large numbers again. We get 1 over square root of n as a convergence rate. Okay, so this is the situation again for this very simple linear function. And now let's see what we can do when talking about training neural networks. And so basically optimizing a function which is highly nonlinear. So here are a couple of problems. So if we don't train this quadratic function, but we train a function for which we don't know, is it convex, is it coercive, what's going on, it might happen that this function actually pushes you to infinity. So you keep moving and moving, and then if you take the average, then it just makes you slower, right? So the iterates, they want to move to the right because the smallest value is actually at infinity. But when you take the average pushes you a bit back to the left, and this is not really something that you would hope for. So this is one problem. You don't want the weights of stochastic gradient descent during training to explode. Can we prevent this, or is this something that happens when training a neural network? Then let's say that we stay in a compact set, so we don't explode. Still, do we actually converge? So what might happen is that the set of minima is like a circle, and if we converge to the set, but we don't converge like to a specific point, then it might happen that we move around the circle infinitely often, which is not bad. So it's close to the set of minima, so the loss might be very small. But if I take the average, then I land in the middle of the circle, and there might be a very high loss. Okay, so if I don't converge, averaging shouldn't give you anything. It should be good. Those two we can rule out in some settings, and if we can rule them out, then the question is, now we have a loss landscape which is highly non-quadratic. Can we still gain anything from doing this average over all the iterates? So can we still derive some convergence rate for now the stochastic gradient descent scheme on a very, very general function? Okay, so this is a line of research that I did together with Steffen Derek and Arnold Jensen. And here are a couple of results. So I will present them very broadly, very generally, so without the specific assumptions, but this is more or less what we did. So the first one, can we explode? And for this, we looked at a very basic shallow neural network with ReLU activation function. And basically we showed the following. So if we have a typical regression problem, and our regression function is a shallow neural network with ReLU function as activation function, then generally there exists a point within the search space which is the global minimum. Yeah? So a point which actually attains the infimum. So in general, it might happen that the infimum is at infinity. So if I let the weights and biases explode, then I get a neural network which somehow performs better than all the neural networks that I would get for finite weights. Yeah? So it might happen that this infimum is attained when I take a sequence which goes to infinity, then it's strictly decreasing and goes to the minimal value. But this is typically not the case. So how does it work? So here we do a bit of algebra. So basically we talk about hyperplane arrangements and functions that are partly affine linear. And what you can do is you can think of what kind of strange functions can I construct by letting my weights explode. And the response function of a neural network is always a continuous, piecewise affine function. But if I let the weights explode to infinity in a very strange way, I can construct functions that are non-continuous. And so basically we showed that these are the functions that you can get in the limit, and these functions are not optimal when doing your typical regression task. So by this we ruled out that there is a neural network in the limit that performs the best, and then in order to do our minimization task, we have to converge to this limit point. So this is a simple example where we showed, okay, we can solve the optimization task within our search space without the weights blowing up. So this is the result for the first problem. For the second problem, now let's say we stay in a compact set. Do we actually converge? And this is not easy because there are some functions, for example, this so-called Mexican head function. When you follow the gradient flow, then it basically goes in a circle infinitely often. Yeah? So you would converge to the unit circle in the limit, but actually it goes around infinitely often and doesn't converge to a specific point in the circle. This is a problem which you can rule out by just assuming that the objective function is analytic. So with this, there's a lot of geometric results. There are the so-called Lujasiewicz inequalities, so some gradient inequalities, and they tell you that the gradient flow on an analytic function, if you stay in a compact set, converges to a point. Okay, and now we did this for stochastic gradient descent. So basically we took the gradient flow, we discretized it, and we added some randomness. And we showed that as long as the step size decay fast enough, so now you are not allowed to take gamma between 1/2 and 1, but it should be between 2/3 and 1. But if they decay fast enough, then you can carry over this deterministic result and get convergence to a point. But since we have a stochastic process, it is a random point. Yeah? So for each omega, this converges, and we denote the limit by theta infinity. Okay. So we have shown that in some situations we don't explode. If we don't explode, then typically if the objective function is analytic, then we actually converge to one point. And now here's the CLT result. So if we have an analytic objective function, then most of the time, so for many of these objective functions, the set of minima will form manifold. And then you can do stochastic gradient descent. You converge to one point on this manifold, and you have now two specific directions. So you have the tangential directions and you have the normal directions. In the tangential directions, the function is constant, so the gradient should be 0, so there's not really a restoring force. And in the normal directions, this function looks like a quadratic function. It looks like a strongly convex function. And if we have this, then we can do our averaging. Since we converge to a specific point, also all the iterates more or less cluster around this point late in time. And again, we recover the fast convergence rate from the classical CLT for quadratic functions. So now we talk about the objective function value, because this looks like x squared. This doesn't converge like 1 over square root of n, but 1 over n. But this, again, more or less tells you that if you do stochastic gradient descent on a very general analytic function, you get a CLT, so this converges to some kind of Gaussian, and it has the right convergence rate, so we don't lose anything from going to this more general situation. All right, so these were 3 results that somehow carry over the classical stochastics result that we will see in the first course of stochastics to a training of neural networks. And yeah, that's it.